So welcome to those who are joining us on YouTube. But we're going over right now. We are thinking about the notes from Tuesday, where we had some negative conditions on bipartite graphs. We decided that if you look at a cycle and you think about its bipartiteness, right? It has the bipartite sets that are the same size. So as you go around, if you have an odd cycle, it's not going to be bipartite. And if you have an even cycle, then the sizes of the partite sets are always going to be the same, right? So we see an example here where it's 2 and 2, it's 3 and 3. So if you embed this into a bipartite graph, this is going to be all the vertices, so the partite sets are going to have to be the same size. You want to say hi to everybody? You want to come say hi? Okay. You're going to graph theory today? All right, so then it changes a little bit when you have a path, because paths are always bipartite, but the sizes of the partite sets change. So if you have an even length path, the sizes will be the same. If you have an odd length path, the sizes will be off by 1. So we see those two examples here. And so if the partite set sizes are off by 2, there's no way that you could embed a path in there, because in a path, the sizes are off by 1 or 0. Okay, so that was sort of the big idea from class on Tuesday. And okay, so where do I want to go? I want to think about, okay, there's some technical difficulties here, but we're going to bring up our notes, and then I'm going to put us all into breakout rooms. All right. Working from home is going well. Okay, so we're going to bring up the notes. I have to, again, log into Blackboard, unfortunately. But we'll bring up our notes, and actually, wait a second. I think I have them right here. So we're going to start here. I'm going to put us into breakout rooms, and what we'll do is we will start here with question G7. And so we'll work for a little while today. We're a little bit ahead, and then I will I'll bring us all back together here in a little bit. Okay, so let's do some breakout rooms. So we're gonna go. There'll be 3 different rooms, and you'll be in with either 3 or 4 other people. So we do this, right? It's random. In breakout rooms, they are created for me. So I'm going to open them up, jump it there, and then if you're able to, I think it was pretty helpful to share the whiteboard. So somebody try to share their whiteboard and then collaborate that way. So here I'm gonna open them all up, and then so start thinking question G7, and I'll jump into the breakout rooms as we go.
So we're starting with 7, right?
Yeah.
7, yeah.
Oh, word, what up?
Hello. All right, we're getting set up here.
Yeah.
Did this work out pretty well last time with the whiteboard and everything? It seems like it was okay.
I like
Yeah,
it better
I think
than
it's
not
better with
having it for
the-
sure.
Yeah. We can write on this, right? Yeah.
Yeah, you can all write on it.
I mean, so it's definitely no, because a graph can be disconnected and be bipartite, but it can't have a Hamiltonian cycle if it's disconnected.
Exactly. Yeah, so that's it. To answer the question, that's absolutely right. So what if I sent it back to you and said, what if I put a connected condition in here? Is it true? No?
My gut says yes, but like,
So a connected bipartite graph with an equal number of vertices must contain a Hamilton cycle.
Yeah.
Yes, that's for sure.
All
I
right,
don't have
then.
any proof, but I agree.
Okay, well, prove it. Try to prove it. And then if you can't, try to find a counterexample. But yeah, you're right. So if it's disconnected, you're absolutely right. If it's connected, could you come up with one that doesn't?
I don't like what I'm
This
doing
whole
right there.
time,
Yeah, think about it.
I
see what
have a
you get.
counterexample.
You have a counterexample?
Yeah, you could do a path, right? And then it wouldn't have to have a cycle on it.
Ooh,
Mm.
smart.
Any path, right? Yep.
Bam, bam.
Yep.
All right, no.
Yeah, big old. Nah, not this time.
Yeah.
No, yeah. All right, I keep going. I'm gonna check in with some of the other rooms.
Come on.
Uh,
There we go.
Edwin screen. Okay, here we go.
Yeah, that's what I was saying too. Cool. All right. Hey there.
How are things? Things are good, bad?
Good.
Going.
Yes.
I found it's easiest to print the notes out still, rather than
Yeah.
being on the screen.
Yeah. Do you have a printer?
Yeah.
Yeah.
I don't. So
I
that's
don't have a printer either.
Yeah. I have a printer. It doesn't have any ink in it. So
Okay.
effectively I have a scanner.
yeah.
Yeah. So I'm in the same boat. I'm all digital now. So okay, so what we've been thinking about 7. Got any ideas?
We just finished 8,
Yes.
What'd you say about 7?
7.
Mm-hmm.
That's kind of what we were indirectly just going over. It doesn't necessarily have to have one, but it could.
So can you give a counterexample?
I could probably think of one if you gave me a moment.
Bipartite graph, equal number of vertices of each color. Does it have a Hamilton cycle?
I think it's a yes, like always.
I think well, if the partite sets are the same size, then it definitely has a cycle.
Yeah. I thought that's
All right, we have 2 differing perspectives here, right? So Matt, your job's a little bit harder because you're gonna have to prove your claim.
yeah.
Dan, yours is you have to throw out a counterexample, right? If you think yours is true.
Yep, I'll figure it out.
All right, and then you thought about 8.
Yeah.
So for 8, we talked about so for A, suppose you cut a string k points, you're gonna have k plus 1 pieces, and then for B, if it's a loop, for every k cuts, you'll have k pieces. So like if you cut a loop once, there's still 1 piece left,
Yeah.
kind of deal. Is that what you're looking for? Is that what you're talking about?
Exactly right. Yeah. So if you have a rubber band and you cut it, you get 1 piece, right? You still have 1 piece. If you have a piece of string and you cut it, you'll get 2, right?
Okay.
So if I cut a piece of string 5 times, how many pieces do I get?
6,
6. And if I cut a rubber band 5 times, I would get
5.
5, right? Yeah. Yep. And so what we're going to do is what you're going to think about is like when you think about a graph, a rubber band, that would be like a cycle, right? All the vertices would be on the rubber band. And when you cut the band, we're going to think about like deleting a vertex in the graph. And then we're going to start to think about, hey, how many components should I be able to get? So if I had a path, like if you go down to G10, there's a path there. So they're going to ask you questions like, hey, what happens if I start deleting vertices? How many components should I be able to get in my graph? We're gonna start thinking about things like that, right? So again, negative conditions. Could you come up with something where, right? Could you come up with something where the like if I delete so many vertices, what if it has a Hamiltonian path? How many components should I be getting? Things like that, right? So this is going to be called our subgraph condition. And so if you go on to on the next page, so it's after G12, it says subgraph test for Hamilton paths and cycles. It's gonna be going to this idea of like cutting the graph or deleting vertices and trying to figure out, how many components should there be if there was a Hamiltonian path or a Hamiltonian cycle. Okay.
Okay.
All right. Dan, keep thinking about your counterexample.
I'm working on it.
All right. I'm gonna jump in another room and I'll keep making the rounds.
All right.
Okay.
The number of components.
Yeah.
But there are 1 through k+1 possible components.
Yeah. Okay, I got it.
So in this case, can you remove like 2 vertices of degree 2 for this one? You know what I mean? Like if you had a path of 5 vertices and then you take the 2 that are degree 2 and you remove those, then there's 3 components.
Yeah.
Okay.
It depends on how many vertices there are to remove.
Yeah. Okay.
But
that makes sense. Hi, Professor
Sorry, I'm just trying to get it.
I'm just listening. So yeah, if you remove, I guess you're thinking about G9 here.
Yeah.
Mm-hmm.
If you remove 3 vertices, you could have 1 component, 2 components, 3 components, 4 components.
Mm-hmm.
Is that true?
Well, if you remove a vertex of degree 1, there'll always only be 1 component.
Yeah.
Yeah.
So but I think, John, what you were saying is it goes up, you could have 1 through k+1, right? So here's a path. I can remove 3 vertices, and I can have 1, 2, 3, or 4 components after I remove 3 vertices.
Yeah.
no.
Oh.
I think that's what John said, but that's
It is.
not. I don't think I could make 4 components, right?
Yeah. I think at most you could make 3 components.
I agree.
By removing 3 vertices.
By removing 2 vertices.
2 vertices, yeah, you could get to 3 components.
Yeah, you could
You
remove this
remove
vertice
this one. Yeah.
and this one.
Yeah, so what's the difference between 2 and 3 in this case?
2 and 3 what?
Like, so removing 2 vertices, you can get 3 components.
But if you remove 3, you get 2.
Yeah,
components.
Can you remove 3 vertices and get 3 components?
No.
No.
So the possibilities for 3 are only 1 and 2.
Yeah.
So like, what's so different from 2 to 3 in this case?
I think it has to do with the size of our path, like the number of vertices in our path.
Yeah, and then so there's 5.
Is it because our max degree is 2, we can only remove up to 2 vertices to make the maximum amount of components?
I don't think so. I think 2 has to do with in relation to 5 and not the degrees of the vertices.
No. Oh, yeah, I see.
5 minus 3 is 2, and 5 minus 2 is 3.
Yeah,
I
right.
don't know.
Yeah.
That's what I'm thinking.
Yeah.
Only pattern
yeah.
I see.
Yeah, so right, 5 minus 2 is 3, and then 5 minus 3 is
2 components. So it's like your number of vertices minus the number of vertices that you remove equals the max number of components.
Well, I think what John said, I don't think John is wrong. He just needs to put a caveat on what he said.
I was thinking of it as an infinite path. That's why I said it.
Ah, all right. If it's an infinite path, then yeah, I think you can do that if it's infinite. But if it's a finite path, then what's up? So I was thinking it the way I'm thinking of it as 2 is less than half of 5,
Mhm.
and 3 is more than half of 5.
Yeah.
So once I start removing more than half of the vertices, we're going to have some problems, right? Because the maximum number of components that I could have here is the number of vertices, right? So if I deleted all the edges, I would have at most 5 components. I couldn't ever have any more than 5. But every time I delete a vertex, I lose a maximum number of components that I could have. So by deleting 3 vertices, the maximum number of components that I could have is
Oh.
2, right?
Okay.
So, Kirsten, what you were saying about is 5 minus 3, that's really important, right? So if I take away 3 vertices, the maximum number of components that I could have is
5
2.
minus 3. Yeah. Okay.
So there's going to be a couple cases here, right? So one case is going to be, hey, if you're deleting more than half of the vertices, and if you're deleting less than half of the vertices. I think you're going to have 2 cases. One case, John, you're going to be right in one of those cases, and then the other case, you're going to have to think about something else.
Okay.
Does that make sense what we're doing here?
Yes.
Okay. All right. Did you think about 7 and 8? What did you say for 7?
Not necessarily.
Okay, it doesn't have to. So can you come up with a counter? Did you come up with a counter example?
A path that
Yeah,
has
right.
an even number of vertices.
Yep, any even path. Exactly right.
Okay.
Okay, excellent. All right, cool. I think you're all doing great here.
Thank you.
Any questions for me so far? All right, I'm gonna keep making the rounds. Keep going.
Okay.
You're doing great.
Perfect. Thank you.
Oh, hello.
Well, hello. Min maxes. I like this over here. Tell me about it.
So that's for the path.
Uh-huh.
So if a graph consists of a simple path and k vertices are removed, it will contain at minimum, well, I mean, I guess 0 components at minimum if you removed all the vertices, right?
Uh-huh.
So I mean, but minimum of 1 if you like don't remove everything.
If you just remove one thing, yeah.
Yeah, right. And that would be if you remove only the end points, right? All the way down. And the max would be the ceiling of k over 2 because
if you take like the center point, like one of the vertices from the center, you'll take the incident edges as well. So you'll create well, depending on the number of vertices, you'll create 2 components, and then from there you just keep taking the center points, and you'll have whatever amount of components.
Yeah, if you take every other one, you're either gonna get half of them left if it's even, or if you take like every other one, shifted one over, you're gonna take half of them, rounded up if it's odd.
Yeah.
So like if we take for example, if we take like one of these vertices with 2 incident edges, so we'll have 2 components.
Yeah.
And then if we take like another vertex,
yeah,
then we'll have 3 components, and then
you can take either one.
Yeah, and you take the one to the left, I think, just for the sake of the. Yeah.
Right. Yeah. But what they're saying is all the possibilities. So if you have a path of length 5, okay, so we'll keep your path of length 5 here. Okay, so we've got this. Now, what you demonstrated was the maximum, but can you do it where you have could you delete, say, 2 vertices and you only have 1 component? Can you delete 2 vertices and have 2 components? Can you delete 2 vertices and have 3 components?
Oh,
Can you delete 2 vertices and have 4 components?
okay.
If you take this one, you'll have 3 components.
You can have 3, yeah. Can you have
yeah,
2?
yeah. You can have 1, 2, or 3. You can't have 4 because 3 is the maximum.
1, 2, or 3. Yeah. So if you have 2, right? In this case, if I take away 2, I could make it 1 component, 2 components, or 3 components.
Yeah.
What if I did 3?
If you took away 3,
Huh?
you would have either 1 component, 2
Alright.
components. I think 1 or 2 components.
Yeah. Why do you think that is?
So if we took this one, you would have 2 components. If we take this one, you'll have 3.
Then you just have to take any of the remaining 3.
And then you could just take, yeah, so like, let's see. So if we took 3, that'll be 2. That's 1 vertex. Yeah, so we'll have, and then if we take another one, we'll just have 2.
So you could have 2. So Edwin, you demonstrated we could have 2. My question is, could you make it so that you have 3?
All right, so
No,
Yeah, I feel like no. By taking away 3 vertices.
because I was gonna say you only have so many vertices and edges right there, like
Because-
total component or total whatever you want to call it. So there's like what 5 vertices and 2, 4 edges. If you take away 3 things, bare
Yeah.
minimum, that's gonna take away 6 total things, like edges and vertices.
yeah,
You
so I
can't
don't,
make that into more than a 2-component thing.
let's see, take,
So you're thinking about edges too, but in a path, do the edges? Remember your graph? Your whole graph is a path. So do the edges really matter?
Mm,
Well,
Well, like yeah,
depends
how
if
many
you
components
so-
you make.
so the way I'm thinking about it a little bit, is like if you need to take away really every component at minimum is going to be at least 1 vertex, right?
Yes.
So if you take away 3 vertices
only
from a
left.
path with only 5 vertices, you'll only have 2 vertices left, and because each component has to have at least 1 vertex, you can only possibly have 2 components.
Right. At most, right?
Yeah.
So if you have 5 vertices, you take away 3, you can have at most
2.
2 components. Can you generalize that?
so wouldn't that just be like n minus k?
Yeah. N minus k. So what is that, Edmund?
So the number of vertices minus the number of vertices you remove.
Is what?
The number of components you can have as a max.
The max, right? Max number of components. Okay.
Yeah.
So do you think you can get every possibility from 1 up into the max?
Yeah, probably. I don't see why not.
So I mean, let's keep trying. So for 3, you got 1 and 2. So let's try a path that's a little bit longer, right? So let's try say just 1 more. We'll make it 6. We'll add another edge in here. So 1, 2, 3, 4, 5, 6. What if we have? Let's think here. So if I remove 1 vertex, the maximum number of components that I could have is 5.
Yeah.
Can I get anywhere from 1 to 5 components?
No.
No. My only possibilities are 1
1 or 2.
or 2. Okay. So what if I did 2?
You could have 1, 2, or 3.
3, yeah.
1, 2, or 3, right? Yeah. Okay. And what if I did 3?
So is it if it's higher than half of the number of things? Because if you have 3, I think you can only do 1 or 2 again.
Yeah, you can only do up to 2.
Yeah, so if it's higher, right? So the way that one way that we could think about this is you could say the possibilities right, you could have 1, 2, all the way up until what?
Up until
plus one?
3. 3 is the maximum you can have.
Yeah, so could you think you can go all the way up to k plus 1? Sometimes, right?
Are you asking if we can take away k plus 1 vertices?
No, you're taking away k vertices, and then the question is how many components? Could you get k plus 1 components every time?
No.
Sometimes, right? Sometimes you can get to k plus 1.
Yeah. But not every time.
Not every time.
Odd.
So what's the other idea?
As long as k is less than half of the number of vertices.
Okay. What about when it's greater than?
Then it's just going to be k n minus k,
Yeah.
right? I think. If it feels right.
Like this?
What am I looking at?
Yeah, we don't see
Yeah.
anything, I don't think.
You don't see my text here?
No.
No.
You don't see any of this?
Oh, I see that now.
Where?
Is that where it says
yeah, I
n
see that
vertices,
too.
remove k of them?
Yeah.
Okay.
Oh, yeah.
Okay,
Oh
okay,
no,
okay.
there we go. Okay.
Yeah.
What happened? It didn't show up for you?
Well,
Just
yeah,
popped up
possibility
now.
for components 1, 2,
Oh, I have to hit enter or something for it to come up?
I don't know. I just got it like a second ago.
Yeah.
Oh man, sorry.
That's okay.
Can I move this text? We're all learning here. We're all learning
For
here.
sure.
All right, but you can see this now.
Yeah, I can see it now.
Okay. Does this make sense? Yeah.
Yeah.
All right. I mean, things are kind of getting a mess here. Another way that we could write this is you could have 1, 2, up to the minimum of k plus 1 and n minus k. Did this show up here?
Yeah.
Yeah,
Yeah, the bottom like left.
Yeah, so if you wanna think about this as a one statement thing, you're gonna have 1, 2, 3, 4, and you could go all the way up to whatever's smaller. Okay, so the smallest of either k plus 1 or n minus k. So n minus k is the maximum number of components. So if that prevents you from getting all the way up to k plus 1, then it does, right? But if you can get up to k plus 1, then you can.
Sweet.
So this would be a nice compact way to write it rather than putting it into cases.
Cool.
So what's the case for cycles now?
We were saying that if you take like one vertex away in a cycle, then you're gonna be just left with a path.
That's right. Yep.
So like you do the same thing, except first take away that first vertex.
It's like cutting a pizza.
Yeah, right. So that's a great way to think about it. You take away a vertex, and then that's going to leave you with a path, and then you have all the possibilities for path.
Yep.
So what you're going to do is replace all your k's in this thing down here with k minus 1s.
Because you took that first.
Yeah.
Min k,
have to
comma,
take
n
that.
minus k minus 1.
Yeah, because then it's like deleting one less vertex from a path.
Yeah, I was just going to say it takes an extra step to turn it into a path.
Yeah, no, that's an awesome way to think about it. That's better than the way that I was going to go. So nice. All right, cool. We're good
Yeah.
with me. I'm gonna go check in with the other room.
All right.
All right.
Sweet.
You know how all this works. Here we go.
Hi again.
Hello.
Hello.
What are you thinking about?
So we're kind of just talking about what vertices need to be taken away for there, within a cycle, for there to be more than one component.
Okay. So in any cycle or a graph with the Hamiltonian cycle?
The graph of the Hamiltonian cycle here. So like we kind of were just taking away, like we noticed that up at the top here, the vertices written out for the Hamiltonian cycle, it was A, or what was it, A, D, and G that were removed, and none of them are adjacent to each other. So if you select vertices that are adjacent to each other when you're deleting them, then it's just going to be one component. But if you are selecting ones that are separate by at least two vertices or something like that, then that's when you can start breaking it up into separate components.
Maybe.
Yeah,
so the thing that's going to get you here is you don't know how many other edges there are, right? So they might be adjacent. So you so let me come up with an example. I'm gonna annotate here. So the best you can say is you can only say that you'll get at most something. You can't say that you're gonna get at least something. So if I have a graph that looks like this, and I'll draw on some edges here. Can y'all see this?
Yep.
Yeah.
So it's going to have a Hamiltonian cycle, but then let's say I have like a chord like this, right? So that goes across the cycle. So if I go ahead, if I delete some stuff, right? So if I delete this vertex and this vertex, I still have a component. I still just have one component, right?
Right.
So all this component down here is still going to be connected, even though I deleted adjacent vertices. Now, if we back this up, I don't necessarily need to have the chord here, right? So I could have something like let's keep the chord. Whoa. Stamp star. Oh, let's do this one. This here. Let's keep that chord going across the middle. So even if my vertices aren't adjacent, if I say delete this vertex and then I delete this vertex, we're still connected, right? We're still one component, even though they weren't adjacent. So you can have these additional edges in here that keep your graph connected, and without knowing more about the graph, you're just not going to know whether these edges are here or not.
Right. Okay.
All right. So that's why we're going to have. That's why when we see this condition, it's going to be like an at least kind of thing.
Okay. So when something's written out like it is, like up here, there could be other edges that aren't listed. This is just specifically talking about the Hamiltonian cycle.
Yeah, so just because you know there's a Hamiltonian cycle doesn't mean you know anything about the connectivity of the other piece of the graph. Yeah.
All right, that makes sense.
So again, remember what we're trying to work up to is this other negative condition for subgraphs. And we'll see that right after G12 there.
Okay.
Okay.
Right.
Okay, so pretty much we want to come up with this condition that says the number of components is at most this, and the number of components is at most this.
Right.
So do you have any ideas for what that's going to be?
Well, I can tell you it's at least 1 or 0.
Yeah. So I have a graph. It's got a Hamiltonian path. I remove 3 vertices, and the maximum number of components that I'm going to see for sure is
3.
You could see 3. You might be able to see more. You're going to say hi. Hi. Do you see everybody over there? Can you say hi? What's your name? Zoe. That's right. Say hi to everybody. Yeah. Are we going to learn with us? What did you bring us? What is that?
A lion.
A lion. What does a lion say? Rawr. You going to help us learn today? Okay. What are you going to do? You're going to go see Mama while we learn here? You're going to take that marker? Can you go give it to Mama? You're going to bring her a lion? Okay. Here. Go bring that to Mama. Thanks for visiting. All right. Thank you. It's the new normal, everybody. The new normal. Okay, so yeah, we want to. So you have a graph that has a Hamiltonian path. You remove 3. You could get 3 components. Could you potentially get more than that?
Yes.
How many more?
No.
I don't think you can. I think it's
No, you
3.
can't. It's the same thing as the rubber band.
Can't get more than 3. No, Hamiltonian path.
Oh, I thought you said cycle.
Cycle, you're right. If you're thinking cycle, then you're right. You can get 3. If it's a path,
I should be able to get 4.
4.
Okay.
Right. Yeah. So it's going to end up being like the same as the rubber band, right? So if you have a path, so basically what we're going to be thinking about is if you can look around in your graph and find a particular set of vertices that you delete them and you get more components than the vertices you deleted, then that could cause some problems for you, right? In regards to Hamiltonianness, paths, or cycles. And so those numbers are going to be right. So for path, if you get more than k+1 components, and if it's a cycle, if you get more than k components,
okay,
then you're in trouble. But yeah, that's what you'll see. That's what you'll see if you scroll down a bit. I don't know who's controlling this. Yeah, the subgraph test.
Okay. This down here?
Yeah.
Oh yeah, that's here.
All right. So think about why would that be? Why would that be true? I didn't give you all an opportunity to ask questions here. Is there any questions for me so far? Things are
so far so good.
Rock and rolling. All right.
Moving along.
I'm gonna make. Let's see. It's 1:40. So I'll probably bring us all back together with 10 minutes to go. We can check in and see what's going on. All right. So I might make it back. We'll see.
Okay.
All right.
All right.
Bye.
So.
I think you should be able
Right.
to move. Yeah.
And then you got 4, right?
Yeah.
Points. Okay.
What are we thinking about?
Now we're just going through the cases in G14 using the what's it called subgraph test.
Does this subgraph test make sense?
Yeah.
You want to tell me about it? Explain how it follows logically. Why does it make sense?
That's the conclusion we came to in G12. That for a cycle, it's k is greater than or equal to k, and for a path, k is less than or equal to k+1.
Yeah, right. So if you have a Hamiltonian path and you delete k vertices, the number of components is always less than or equal to k+1.
Yeah.
And if you have a Hamiltonian
cycle,
the number of components is
less than or equal to K.
K. Yeah. So if you think about, if you flip that on its head, right? So if you had more components than that, necessarily you couldn't have a path or cycle in each case, right? So that's where the K plus 2 comes in for paths, and the K plus 1 comes in for cycles.
Mhm.
And then you're applying it. So I see. Let me see. For the blue. The
blue is the ones we took out.
You took out those two, and then you got
three components.
Yeah, so 2 vertices, 3 components says that there's no
cycle.
There's no cycle. Is there a path?
I haven't checked that yet.
Are we doing D?
D.
Yes, there is.
Yeah. Can you draw on this, John? Or are you?
No, he can't.
I cannot. But start at either one of the degree 2 vertices.
Start at one of the degree 2 vertices. So like this one.
Yep. Go down to the next one.
Yeah. Take that one out or leave it.
No, I'm drawing the path.
Yeah.
I'm having you draw the path.
Okay.
Oh.
Go down, then go right, go up, go to the center, then go to the draw an S. Yeah, like that.
Yeah. Yep. So there's a path, no cycle, right? And so then you demonstrated by deleting the 2 and got 3 components. Yeah.
Yeah.
And then C, it looks like you deleted 4 and you got 5 components.
Yeah.
Yeah.
So there's no cycle. Is there a path?
Yes.
Yeah. You can see there's a bunch of them, right? A bunch of different ways to do it.
Yeah.
Mhm.
Yeah, so there's a path for posterity, right? So here's the one that I saw first. Something like this, right?
Yeah.
Yeah.
That's exactly what we had, John. Pretty
But
much.
you already drew this one in?
Yeah.
Okay, yeah. And then deleting these 4 shows that there's no cycle, or you have 5 components.
Yeah.
What about these 2? Did you already do A and B?
Yeah.
Yeah.
For A, we said if you take out the center vertex, then you get 3 components.
So it's neither a cycle nor a path.
Yep.
Mhm.
And then for B, we said we'll take out these 2 right here.
Mhm.
Makes 4 components.
There's no cycle, no path, right?
Yeah.
Yep.
Yeah, so if you went all the way back up to question 1, those A and B were those 2 graphs were all the way back in question 1.
Oh, yeah.
Yeah, so those are the 2 that we
These
couldn't
2.
find any
Yeah.
for, right?
Yeah.
B and D. So we couldn't find any for those.
Recognize them.
Yeah, and now you have like a reason why there's none, right?
Yeah.
Other than
Yeah.
I just couldn't find any. Now it's like, oh, here's a reason why there's definitely not.
Whoever computer's up on the board right now, you only have 2% battery.
Thank you.
Good catch.
I'm going to have to go downstairs. That's okay.
You need
It'll last for a little bit.
Need a charge.
Yeah.
Okay, but this feels pretty good.
Yeah.
Mm-hmm.
Okay,
Definitely.
so up to this point, what you've found is a lot of ways to say you definitely don't have a Hamiltonian cycle, or
Mm-hmm.
I'm used to calling him Hamiltonian. The book calls him Hamilton. So
that's why he's been saying it this whole
I'm
time.
used to Hamiltonian too. And
Yeah,
I was like,
he's-
am I crazy? Okay.
yeah, I don't know. This author calls him Hamilton. I call him Hamiltonian.
Okay.
But yeah, now we're going to ask the questions like, hey, well, instead of saying no, you don't have one, what conditions say yeah, you do have one? And so when you down here at the bottom, when you say, hey, there's some positive tests, when are you definitely going to have a Hamiltonian cycle?
Okay.
But
Cool.
seems like things are going great.
Yep.
All right, I'm going to keep making rounds. Probably in about another 5 minutes or so, we'll come back together, have everybody
Okay.
check in and see how everything's went.
Perfect.
This is 3. back to 1.
Well, no, but I mean,
Hello.
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 What up?
How are things?
I'm good.
So,
We're on G12 now.
G12.
Mhm.
Okay.
Starting up on it.
You just started thinking about it?
Yep.
Yeah, you can, Edwin, you can erase these if you want. I'll erase these actually.
fill in the blanks. If K vertices are removed from a graph that contains a Hamilton path, then the number of components in the resulting subgraph is. Didn't we just answer this before?
Well, the A took away 3, and there was still one whole component.
Isn't that n minus k?
But B took away 3, and then there was 3 components.
I think it depends on the degree of the vertex.
Points getting taken off because C was degree 3, G was degree
4.
4, J was degree 3, which is a total number of degrees.
Let me see. So, let's do
So what if I'm gonna add some words here to make it so pretty much there's a specific thing that you're looking for here, and so if I can, I'm gonna try to size this. Click out. Can you see this now?
At.
What do you see? All right. Let's try this again. At most, it's supposed to say at most.
Oh, okay. Thought we were doing Sesame Street.
I know. I watch a lot of Sesame Street. Yeah, so the number of components in the resulting subgraph is at most.
n minus k, right?
At most.
N minus k minus 1?
At most.
That's for a cycle.
Well, yeah, but that's the most it could be if it was a Hamiltonian. Oh, path. So it'd be n minus k. Yeah. Okay.
At most. Would it be?
It could be n minus k, but that's only when k is really big, right? What if k is small?
Like if k was 2,
Yeah.
then it would just be 1. You took out.
Most 1 component.
No, wouldn't it be at most 2 components?
If k is 2.
If k is
Or
2,
at
No, it'd
most
be 1.
3 components.
you just have 1 vertex.
Yeah.
If you take away 2 components.
No, if you take out
No,
one
if it only has 2
Oh yeah.
has
Okay.
2
then
vertices.
1, yeah.
So if you take away 2 vertices, the most components you could possibly get is
3.
3. And if you take away 3, the most you could get is
4.
4. And if you take away k, the most you could get is
K plus 1.
k plus 1, right? Yeah, so in this case, right, if you have a Hamilton path, then if you delete k vertices, in any case, you're never, ever going to get more than k plus 1 components.
Yes.
Okay?
Okay.
And what about if you have a cycle?
Just k, right?
You're gonna get k. At most.
At most k.
And then this is going to be
Nice.
at most k, right? Yeah.
Cool.
All right, so k vertices are removed from a graph. The cycle is going to kind of keep it together. It ends up being the rubber band problem again, right? So you cut a rubber band in k places, you're going to get k pieces. Right?
Mm-hmm.
And then if you cut a string into k pieces, at k spots, you're going to get k plus 1, right? So it's just like the string in the rubber band that we saw a little bit earlier.
That makes total sense.
Makes sense.
Yeah.
So scroll down now, and then this is going to turn into a subgraph test. So it gives us a negative test that says, hey, can we definitively say when we do or do not have, Hamiltonian path or Hamiltonian cycle? Okay, so for the first one, if you cut it in k spots, so you delete k vertices and you end up with k plus 2 components, is there any way you could have had a Hamilton path?
Which one are we looking at? Oh, just one. Nice.
This one.
So scroll down, the graph contains a set.
See, this is why I like drawing on the board and seeing it, but like, it's cool here, but it's not the same.
Right? Yeah. It's not. We're just making it work, man.
Wait, so what are we trying to answer? That it can't contain a path, right?
Yeah, we're just we're not. There's no question. The question is,
okay.
doesn't make sense.
Yeah.
So if you cut it and there were k plus 2 components, you could never have a path. And if you cut it, or by cut it I mean delete vertices. If you delete vertices and you get, k plus 1 components, then there could not possibly be a cycle. Because if there were, the max you could get is k.
Mm-hmm.
Okay.
Right?
Makes sense.
Path, the max you could get is k plus 1. Okay, so what you're going to do down here, right? So for these problems, G14, try to find the Hamiltonian paths or cycles if they exist, and then try to use this subgraph test. So for this first one, part A, on the first question in this chapter, you said this has no Hamiltonian path and no Hamiltonian cycle.
Mm-hmm.
To try to use this subgraph test, can you find a set of vertices so that when you delete them, you get a lot of components?
Mm-hmm.
Right. So do you see an example of a set of vertices that when you delete them, you get a bunch of components?
Yeah, you just take away the center one.
Yeah, you take away the
components.
You get 3, yeah.
Draw. Yeah, right. You take away this, you'll get 1, 2, 3 components.
Mm-hmm.
Okay. So k is 1. The number of components is 3. Right, so we're in this case over here. We're in k plus 2 range. So there's not even a Hamiltonian path, and if there's no path,
there's no Hamilton.
So is that just a different way to find if there is a path or a cycle? Like you can look at it that way.
If there's
like
not,
to see if there instead of just going through and starting at a vertex and trying to find like the path or the cycle, you can just do that.
Exactly right. Yeah. So this gives you a way to just say, it gives you a test definitively to say, yeah, there's no. Like before, you probably did, when you looked at it, you were like, well, I tried a lot of stuff. And remember, I think it was you, Eric, you said there's something about that center vertex, you're going to have to use it too many times, right?
Mm-hmm.
Yeah.
So this is a way to formalize that idea. I'm going to have to use this too many times. So because when I delete it, I get too many components, so it's connecting too much stuff together.
Makes sense.
It does make
So is it best to always take the vertex that has the maximum degree? Like for instance, the center one had the max degree. So,
no, I don't. I think you could come up with a counterexample to that. So, so if I added here, so
like if we did letter D.
So imagine, so imagine if I added like all these, right, and then these were all connected over here or something. So you might not necessarily want to take that, right? So if I took this one, I would get 2 components, whereas if I took this one, I get 3 components. So this has degree 6 or something. What does this have degree? This has degree 6, so I need another. Does it make sense what I'm saying here?
Yeah.
So this would be imagine this is a complete graph on 5 vertices, right? So it's all connected, or. All right, so that vertex that I added on there has max degree, but when I delete it, I only get 2 components. Whereas if I picked it up from one, I could have
3 components.
Wait, so okay.
Night night.
Oh, okay, they'll be
Okay, you're gonna say night night to everybody.
Nice.
Night.
Do it. Thanks for visiting. You like to see the people? Yeah. Have a good nappy, okay? Okay.
Okay, I see.
We don't get that in class, right?
No.
All right, so we only got 5 minutes left, so I'm gonna bring everybody back together. I'm gonna close the room so we're running out of time.
Okay.
So I'll bring everybody back together here real quick. Did you all get a note here that said like 60 seconds or something?
Oh,
Yeah.
Yeah.
All right. All right. So when we join the room, we're all muted. But so I think that was pretty productive today. Is everybody back with us? Or yeah, everybody's back here. Cool. All right. So I think, correct me if I'm wrong. I want to make sure that we're all in the same spot here for next time. So we covered all this. We went up through G14, and I think some of us started to think about the positive tests here. I don't think everybody started to think about these. So I think probably where we'll pick up next time is we'll start thinking about this Dirac's theorem and some of these different theorems here. Okay, so on Tuesday we'll pick up with G15. Now, no homework. We don't have homework due this Sunday, right? So the first homework of the new, I don't know what we're calling this, the remote session of the spring 2020 semester. So the first homework's not due till next Sunday, so we can have some time to get through all the Hamiltonian stuff. But good opportunity to go back if you want to revise any of your previous 5 homeworks, right? So take some time to do that. Get those to me, and I'll try to get them back to you. The one thing I ask is just make it a PDF. So email me a PDF, and then I'll mark it up just similar to kind of how we were marking up the screens today. I can do that on my iPad, and I'll email it back to you. And a lot of you now have your papers chosen. So John, at the beginning today, we were picking papers. I don't know. I know you joined a little bit late, but so here I will, once we hang up here, I have a list. So Edwin Ramon, you're gonna do Ramsey theory. Sam, you're gonna do Hadwiger-Nelson, and then Sam and Christian, you've got color me polynomial, chromatic polynomials, and Dan and Matt, which one did you all pick?
Let's try that again, not muted. It was the one with the number file video.
Yeah, I don't remember the name of it.
Yeah, I don't remember the name of it either. But anyways, I already put your names up there. So so I'll put the names up on Ramsey theory and Hadwiger-Nelson. But John, you gotta pick one that you wanna work on.
Okay. I'll email you later today.
All right, perfect. And then, so we won't do presentations next week. We'll try to start them the week after. And so I need some time to sit down and think sort of if there's any logical order, or if we want to put some on the same day. So if 2 groups are going to do coloring problems, then we'll probably put those on the same day, stuff like that. So when I have everybody's papers in, I'll think about some sort of order, and then I'll email it to you. Okay.
Yep.
I enjoyed class today. I like seeing everybody. I'm glad that we have a little bit of synchronous time. It's nice to see everybody's face.
Yeah.
I hope you're all staying safe. Stay home. If you don't have to leave, don't. Right? If you have to leave, be safe.
Yeah.
But we'll all get through it. We'll come back together. We'll meet on Tuesday. So enjoy the weekend. Email me if you got any problems or questions or concerns or anything.
All right.
All right.
Yes, sir.
See ya.
Bye.
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 Go on, guys.
Bye.